So in this problem, we're going to use the 5% rule to solve a typical equilibrium problem. And we're given the problem shown here. Consider the decomposition of NaCl to produce NO and Cl2. At 35 degrees, the equilibrium constant is 1.6 times 10 to the negative 6th. In an experiment, 1 mole of NaCl is placed in a 2-liter flask. Calculate the equilibrium concentrations of the reactants and products. So if we look at this last sentence is really what we're trying to do. We need to find the equilibrium concentration of everything in our reaction. So we're given our reversible reaction. The first thing we're going to do when presented with a problem like this is we should write our equilibrium constant expression. So we're given a value of our equilibrium constant here. And so off on the side, I'm going to write K equals, and remember it's going to be products over reactants, so NO squared, because of the 2 coefficient, times the concentration of Cl2, divided by the concentration of our reactants, NoCl, squared. So there's our expression for our equilibrium constant. When confronted with a problem like this, where we want to find the equilibrium concentrations, the way we're going to go about it is using what we refer to as an ice table. And so underneath our chemical reaction, I'm going to write ice, and ice stands for the initial amounts of everything present. C is the change that's taking place of everything, and then E is the equilibrium concentration of everything. So we can start off with what we know, and we're told that we're starting off with 1 mole of NaCl in a 2-liter flask. And whenever we use an ice table, we want to make sure we are using concentrations in the table. And so the initial concentration of NaCl is 0.50 molar. And I got that by doing 1.0 mole divided by our volume of 2 liters to get 0.5 molar. At the start of our reaction, we have no NO and no Cl2. All we have is reactants. For our change, we're going to be losing some of our reactants because reactants are being converted to products. So the change is going to be negative for all reactants. Now we don't know what the change will be, so we're going to call it minus X. We're going to call it minus X. But because of this 2 coefficient, I'm going to call it minus 2X. On the product side, we're going to be gaining product, and so these are going to be positive amounts. And so for NO, again, because of this coefficient of 2, it's going to be gaining 2X, and Cl2 is a coefficient of 1, so this is just going to be X. What we're going to now do is we're going to come up with an expression for the equilibrium concentrations of everything. And to do this, all we're going to do is add the I row and the C row. So the equilibrium concentration of NaCl will be 0.50 molar minus 2X. For NO, it's going to be 2X. And for Cl2, it's going to be X. Next, we're going to take these expressions for our equilibrium concentrations, and we're going to substitute them into our expression for K. And so we can rewrite our K, and remember, this is where we can put our value. K, we know, is 1.6 times 10 to the minus 6th, and it's equal to the concentration of NO squared. So NO is 2X in parentheses squared times the concentration of Cl2, which is X, divided by the concentration of NoCl, which is 0.50 minus 2X, and that is also squared. So here is our equilibrium constant expression. We now have an equation with one unknown. So the key is now we're just going to solve for X. And we can start to do this a little bit, but one of the things we'll notice is this solving for X is going to get complicated very fast. And so one of the things to know is there's a shortcut we can take to help us solve this style of problem. And this shortcut happens if we consider the meaning of this equilibrium constant. This equilibrium constant, 1.6 times 10 to the minus 6th. So think about what that means. If we come up to a reversible reaction, if this is 10 to the minus 6th, that means this reaction is weighted almost entirely on the reactant side. And we have very, very little product. So what that tells us is when you consider this expression on the bottom, 0.5 minus 2x, what we can do is we can make an assumption. And we're going to assume that really that minus 2x is negligible compared to 0.5. Or stated another way, 0.5 is just much, much, much bigger than minus 2x. And again, we're saying that because this number is very small, so very little of the starting material goes on to product. And so this change is very small. If that's the case, our expression is going to simplify. And so we can rewrite this as 1.6 times 10 to the minus 6th is equal to, and the top becomes 4x cubed over, and now 0.50 squared. And what we did by making that assumption is we simplified the bottom of our fraction to remove that subtraction term and just be 0.50 squared. This becomes a much easier expression for us to solve. We can multiply 0.5 squared to both sides of the equation, and we get 4.0 times 10 to the minus 7th is equal to 4x cubed. So then we'll divide by 4 and then take the cube root, and x ends up being 0.0046. So now we know what x is. Before we go further though, we should check our assumption. And this is the 5% rule. So we're going to check our assumption with the 5% rule. And what this rule states is our assumption is valid as long as what we assumed here, as long as 2x is less than 5% of 0.5. And so to check it, what we're going to do is I'm going to say 2 times 0.0046 divided by 0.5 times 100. So all I did was take a ratio of our assumption, so 2x divided by 0.5 times 100. If we do this out, we get 1.8%. So because this number is less than 5%, we can say our assumption is valid. So now we know what x is. And if we come back up to the top, this equilibrium row gives us expressions for the equilibrium concentrations of everything in our reaction in terms of x. And now we know what x is. So we can come back and just substitute. So NaCl is equal to, and we can see we have our 0.50 minus 2 times 0.0046. And so our concentration of NaCl is going to end up being 0.49 molar to 2 sig figs. The concentration of Cl2 is just equal to x. So in this case, that's 0.0046 molar. And the concentration of NO is equal to 2x, which is equal to 0.0092 molar. So we now know the concentration of all of our reactants and products at equilibrium, and we've completed the problem. Thank you.